We're going to look at heat engines and combustion today. So what's a heat engine? You take fuel, mix it with oxygen, it burns, it gets hot. This expanding gases usually makes work for you. This is burning, combustion, or oxidation, the first part. Oxidation, we mix something with oxygen, it's burning. So we remember this from way back when. PV equals nRT. Pressure times volume is equal to the number of moles times the gas constant times the temperature in kelvins. So when something gets really hot, either the pressure is going to go up if you don't let it expand, or the volume is going to go up if you let it expand. It turns out that work is equal to pressure times volume. So when something gets hot, you can do a lot of work with it as it expands with high pressure in higher volume. So in a heat engine, you have to do some work on the gas compressing it, but then you heat it up, and because it's hotter, you get way more work out of it. So let's take a look, for instance, with the Otto cycle. This is what drives your cars, is that you have an explosion in this piston. It drives the piston down, and it makes the crankshaft go around. That crankshaft is connected to your wheels. Let's take a look at this. The intake valve opens, the piston comes down and pulls in air and fuel. Now it compresses it. We put the work in, and then it blows up and expands very high pressure. The exhaust valve opens and the exhaust goes out. We can watch one more cycle. We put the work in, boom, pressure goes up, we get more work out. We get rid of the exhaust. This is called a four-stroke engine because we have intake is one stroke, compression is the next stroke, power is the third stroke, and then exhaust is the fourth stroke. And in this process, we can think of the chemical potential energy of the gasoline turning to heat, which makes the explosion, which turns to work, which is what drives the piston down and it drives the crankshaft around. So we remember from physics maybe that work is equal to force times distance. But power is the rate of work that you do, or work divided by time. And so this would be, instead of force times distance, it would be force times speed. And so power can be thought of as a force term times a speed term. So for rotational power, it's going to be torque times rotation rate. Torque is how hard you're trying to turn something. So the power you put out on your bicycle is how hard you're pushing your legs around times how fast your legs are going around. Power for fluid is going to be how much pressure is pushing the gas times the rate at which the gas flows, or the water in this, if the case may be water flowing. And we'll learn later that electrical power is how hard you're pushing the electricity, the voltage, times the rate of current flow, of electron flow. So let's take a look at another cycle, the Brayton cycle, or a jet engine, or a gas turbine. What you do is you suck in the air, and this is where you do the work. And then you start it on fire, you put in some fuel and it burns. So it's really hot, you have a lot of expansion there, and that gas comes out very fast. And so the heat energy turns to three things. It turns to rotational energy of the shaft, it turns to the speed of the gas coming out the back, and to some waste heat in the back, because the back of a jet engine is going to be hot. Now what you really see for a true jet engine, this part here is down here, where you're compressing the gas. But the shaft is connected to this turbofan in front, which pulls more air in and pushes it out. And this also propels the jet forward. This turbofan is what you see when you look in a jet engine. Don't get too close. So we can generate electricity with this Brayton cycle, with this jet engine. What we have is we have an air intake here, we compress it. Under high pressure here, we add either oil or natural gas. Then it burns and expands out the exhaust. And so that heat, because you heat it here, you're pumping way more volume of gas out than came in because the gas expands. Now, the efficiency limitation in a Brayton cycle, in a jet engine, is there's still a lot of heat in that exhaust. And so we don't turn all of it into, in this case, electricity. And we talk about how we can use that exhaust heat later. So in this situation, we're not trying to move an airplane. We want the energy to go into the shaft. It rotates, turns a generator, and generates electricity. This is where a lot of our electricity comes from. A Rankine cycle is a steam turbine. Rather than heat gas, we heat water. And so we heat water, it boils, turns into steam, and turns a turbine, and it goes around again. Now, it's very important we condense the steam back into water because we want this to be lower pressure, so we have high pressure on one side of the turbine and low pressure on the other side of the turbine. And that's what drives the turbine to generate electricity, potentially in this case. So how does this look in real life? Well, so what if we had a coal-fired power plant? This is a spot that's really hot. We boil the water and turn it to steam. This is a spot we need to be very cold. This part we would put in the Pacific Ocean, for instance. So if you ever wondered, why did we put a nuclear reactor right on the Pacific Ocean next to San Luis Obispo? The reason is because we needed this part to be very cold, so we had high pressure there, low pressure here, and that pressure difference across the turbine is what drives the turbine in a circle to generate electricity. Now, how do we get from the low pressure side back to the high pressure side? We do need a pump here. And so this is where we put the little bit of work into the engine. Now, it's just a little bit of work. Why? Because water has a very low volume, so we have to pump across a high pressure to put the water into the high pressure side. But then we boil it, and it comes out steam and expands, about 1,000-fold. So the pressure difference increases with temperature difference, and we put some energy in, but the water volume is small. Now, one of the very neat things about the Rankine cycle is we can heat this any way we want. We can use coal, which is what's done in about half of the facilities in the United States. We can use natural gas, which is cleaner. We can use nuclear energy. We could use concentrated sunlight. You could rub your hands. You could do anything to make that warm. Now, the efficiency limitation here is different than the Brayton cycle. In these pipes, we have very high pressure steam, and it's very high temperature. And so the problem is, how do we contain that? Because the metal, we don't want the metal to break. And so we can't get this too hot because it will cause the rupture of these pipes. So the lower temperature that we need to keep here is the limitation to our efficiency. So the problem is the Brayton cycle runs too hot and we lose heat, and the Rankine cycle can't get very hot. So what could we do between these two to make more efficiency? And that's the combined cycle, where we have a Brayton cycle, a jet engine, that gets really hot, and its waste heat drives the Rankine cycle. So the waste heat from the Brayton cycle boils the water in the Rankine cycle. And so you have very high heat, the fuel you put in. Then you have a medium heat, which is the waste heat from the Brayton cycle into the Rankine cycle. And so this is really hot, just kind of hot. So the efficiency of a Brayton cycle could be 40%, and the efficiency of a Rankine cycle might be 30%. So what's the total efficiency? Do you just add them? No, that actually, if they were higher efficiency, you could potentially get over 100%. That's not correct. The correct formula is the efficiency of the Brayton plus the efficiency of the Rankine times 1 minus the efficiency of the Brayton. Why is that? Well, we can see it if you start with 100 joules of heat in the Brayton cycle, and then you'd get, with the efficiency of 40%, you'd get 40 joules out here and only 18 joules out here. That's 58 joules out. 58 divided by 100 is 58%. But why is this only 18 joules and not 30? Well, it's because we only started with 60 joules left over, after 40 joules of this 100 joules was turned to work. And so 60 joules times 0.3 is 18. And the total waste heat then turned out is 42 joules.